what is photometric classification? So what I'm showing here on the left side is probably familiar to the vast majority of people. But do I have a laser pointer? Oh, cool. Oh, I'm really bad at using laser pointers. It's fine. The left thing is a simulated LSST type 1A supernova light curve in the 6 LSST observing bands. And this photometric classification algorithm is simply sort of, to an outsider, like a black box thing that eventually hopefully spits out something about what types of object you're looking at. So maybe it's a type 1A supernova, maybe it's a superluminous supernova, maybe it's not even a supernova at all. And to this end, my collaborators and I developed something called SCONE, which is a convolutional neural network for supernova classification. So how this works is that we take the active season highlighted in green here where the supernova is actually occurring, and then we perform this two-dimensional Gaussian process regression in both time and wavelength space to produce a smooth spectral surface, which I'm showing here in the three-dimensional plot with flux on the z-axis. And finally, we sort of fly over this three-dimensional plot and look at it from the top down, or equivalently, you can think about it as coloring this time and wavelength space by flux value. And you end up with this two-dimensional sort of image-looking thing. And in fact, this thing, along with the Gaussian process prediction errors at each point in time and wavelength space, these are the input to our convolutional neural network. And here I'm showing some examples of these flux images or these flux heat maps for the 6 different supernova types that we tested this model on. And you can really see that there's a lot of intrinsic diversity between these images, these representations. For example, the right top one is a superluminous supernova, and you can see that the yellow area, which is the high flux region, the area where the supernova is actually occurring, is much, lower down, which corresponds to higher wavelengths, and is also pretty diffuse, so it kind of lasts a long time compared to some of the other ones, which look like much narrower, which means they last for a much shorter time, and they also, occur at different, the main, light occurs at different wavelengths. So these are all things that we can pick out with our own eyes, and hopefully our artificially intelligent eyes will be able to do the same. And in fact, we find that SCONE performs really well on both simulations and real data. What I'm showing here is probably a familiar diagram at this point. It's called a confusion matrix. And here I'm showing the results for type 1A versus non-1A classification. And the main diagonal just shows the true positive rates for type 1A and non-1A. So SCONE performs really accurately. We have around 99% accuracy on simulations, which is what I'm showing here. And we also tested on 568 spectroscopically confirmed dark energy survey supernova, and we got around a 93% accuracy on the real data. Not only is it accurate, it's also very fast. These results were obtained by training with only around 40,000 supernovae, which takes around 15 minutes on a single GPU, whereas other approaches require millions of supernovae and hours of training time. And as a result, SCONE has been used in dark energy survey, LSST, and Roman analyses. Okay, so I've been talking a lot about, retrospective classification. We already have the supernovas already, done. We have like all of the data about it. Maybe that's a pretty, simple problem, whatever. Maybe people in this room are much more interested in the problem of early time classification. We know that with lots of interesting talk about anomaly detection, finding these rare gems, like we want to be able to do that in real time when we still have the opportunity to follow these objects up while they're still in the sky. And this type of work is going to be vital for optimal allocation of the limited spectroscopic resources that we have. So in fact, we tested SCONE on this early time classification problem. And that's what I'm showing here on the left side, which is a plot of accuracy as a function of the number of days after trigger, where trigger is just defined as like, whoa, something is happening in the sky. That's cool. And you can see that around 0 days after trigger, where there are only a couple of data points, maybe in a couple of different bands, we can do 75% average accuracy across 6 different supernova types on the night of trigger. And that obviously only increases as the number of days goes on, you get more data. But 75% with like very little data is really impressive and definitely will be important for this allocation of spectroscopic resources. Okay, so again, another disclaimer, we've been talking a lot about simulations because LSST is still not around, and so a lot of the things that we have to do are all based on simulations. However, we all know, people who have worked with simulations all know that it's really hard to get simulations to like very closely match up with real data. So what if we actually wanted to train a model with real data? Um, Obviously the most important problem that everyone is familiar with is that it's really, really hard to get labeled data for real data. And in this example, which is this plastic classification task, there's only around 0.1% labeled. So that's around 7,000 light curves. And that's not enough to train really very many models at all. But another more, I guess, subtle problem is that this labeled subset, which typically comes from spectroscopy, is very unrepresentative of the full data set. And that makes it very bad for training. And what I mean by that, I'm showing on the right side. So the blue region is the full data set, and the green line is the labeled data set. And these are redshift distributions. So you can see that the labeled data set is much lower redshift than the blue region, which means that the model, if you train the model on this green line data set, then it won't get to see very many high redshift examples at all. And the problem with that is that, when you give when you want the model to predict on this blue region, then it's going to be very confused by all of the high redshift examples it's going to see in there, because it hasn't had much information about that part of parameter space. Okay, so if you just simply ignore all of the problems that I just talked about and do this training anyway, so just to clarify, you train with this green line data set, which has only around 7,000 things. It's not enough data, and it's also, a very unrepresentative subset. So those are the main issues. So what happens when you do this training and then you test it on this blue region? You get this point here, which I've labeled baseline. And this is, again, on 14 transient and variable object types. So a much more realistic and difficult problem than just doing type 1A versus non-1A. And the y-axis is the accuracy on the full data set. So you can see that it's doing around like 61% accuracy. And we do have a state-of-the-art result for this data set, which is the red line, and that's around 77%. So you can clearly see that there's a lot of, space for improvement, but also we ignored all of the problems that I just talked about. So what kinds of things can we do to improve this performance? So one thing we could do is augment these light curves. So augment the light curves from the spectroscopic data to more closely resemble the data from the full data set. So we know that the spectroscopic data mainly differs from the full data set by the redshift. So like there are many, many more low redshift objects, and we sort of want more high redshift objects. So what if we could just take the spectroscopic data, for example, this one on the left, and pretend that it's at a higher redshift, which is the middle one, recalculate all of its fluxes, like flux measurements and everything based on that new redshift. We know how redshift affects light. And you can see that this middle augmented version much more closely resembles this example from the full data set that I pulled, because they're much more similar in redshift. Okay, so what happens when you do that is you create this new orange line here that didn't exist before. Now this orange line is our new augmented, our new redshifted data set. And you can see that it much more clearly matches the blue region than the green line. So that's really great. And what we want to do with that, of course, is to train this model. So just as a reminder of how that works, typically this is supervised training. So we take these input light curves. It's a pair of information, the light curve and the label. So like type 1A supernova, type 2 supernova, AGN, whatever, you put these information into a model, and then you tried to get the model to predict the label, so type 1a supernova or whatever, as well as possible. Okay, so what happens if you take this augmented data set and train a model with that? So now I've added a new point on this plot called redshifted. And clearly we've made some improvements. Now we're at like 7% or whatever. And that is because we solved one of the problems that I mentioned, which is that we have this this mismatch between the redshift distributions of the training and the test set. Okay, but we still have this other problem, which is that we only used around 0.1% of the data. And there's this other 99.9% of the data lying around that we haven't used because it doesn't have any labels. So what can we do with that? We developed this model, this framework called Connect Later, which is able to incorporate both labeled and unlabeled data. And so how that works is that we add this new pre-training step, which I'm showing on the top row here. And pre-training, I guess what I mean by that is that you use this unlabeled data to train this model, but you're doing an intermediate, you're training it for an intermediate objective. And in this case, we're doing masked autoencoding or mass reconstruction. And instead of training it to predict labels. And that may seem a little counterintuitive, but that's because we don't have any labels for this first step. We have the 99.9% of data that doesn't have any labels. So the benefit of this first step is that you get to train this model with much more data. But I guess the downside is that you're training it for a different purpose. So you're training it to do this mass reconstruction, which is what I'm showing here. And then the next step is that you take this already pre-trained model and then you continue to train it on this actual task of predicting the label that we've been talking about this whole time. So in fact, we find that Connect Later, this two-step training paradigm, improves on, our baseline, simply training on the redshifted data set, and it also improves on the state of the art, which is the winner of the plastic competition called Avocado. And Connect Later actually is a general framework that is agnostic to architecture problem. We've tested it, this is an astronomical example, but we've also tested it on examples like wildlife classification from images and tumor detection from histopathology slides, and we find that it beats the state of the art on all of these different tasks that we tried. Okay, now let's shift gears a bit back to photometric redshift estimation, which is the other major problem that I mentioned when I was talking about how we can transition from relying on spectroscopy for cosmology and moving towards photometry. So this is a very similar problem to classification. Instead of giving you sort of a discretized, like this is a type 1a supernova, this is a type 2 supernova, we're looking for sort of like a real number and hopefully some kind of uncertainty or PDF associated with that. And one thing that we sort of noticed when we were working with these image representations that we created for SCOAN is that these image representations actually make the redshift visible in a very unique way. And so what I'm showing on from left to right is a low, medium, and high redshift supernova. And you can clearly see that although the light curves themselves sort of look vaguely similar, the image representations, you can watch the physical effects of redshifting happen. So you can see that this yellow region starts out very narrow and sort of like towards the top of the image, which is lower wavelengths. And then as you increase in redshift, this yellow region gets more diffuse and also moves downward towards higher wavelengths, which is all what we would expect from what happens when you redshift light. So that's really exciting. And as a result of that, we decided to create this model called photosynthesis. And we call that converting type 1a supernova light curves to redshift PDFs. So the benefit here is that you actually get a discretized PDF out of these images. And here, of course, I'm showing a very good example where the true and the predicted point estimates are very close to each other. But we tested these on real data from SDSS, as well as simulations. And our predictions are these orange and blue lines. These are two different ways of getting the point estimate from a PDF, but they're very similar to each other. And the green line is this baseline that we use often in the field called LC fit plus Z, a very different, template fitting, like Monte Carlo type of approach. And you can see that our estimates are both less biased and more constrained than the LC fit plus Z estimates for both simulated and real data. And that our estimates, at least the binned averages, stay within 1% of the true value across the redshift range. And this is similar in quality to the best galaxy photo-Zs. And of course, we also tested on LSST simulations, and we see that our estimates still lie within around 1%, even though LSST has a much wider redshift range, which is really exciting. Okay, in summary, Rubin supernova cosmology will depend on photometric estimates of supernova type and of redshift. And I've worked on, various things to try to make that happen for us all in the future. Thanks.